Hello, welcome to the lecture series of Analog Electronic Circuits. My name is LEC2 Kumar, Assistant Professor, G Polarity Engineering College, Department of EC. In the lecture 1, we discussed about the importance of what is the need of faithful amplification and what are the conditions we require in the faithful amplification. In order to achieve faithful amplification, what type of biasing we have to give, how much biasing value we have to maintain. After giving the biasing, what will be the effect on the transistor characteristics? To find out the actual effect on the transistor characteristics, after giving the biasing, we required an operating point and the DC load line. So in the previous session of lecture 1, we discussed about the faithful amplification and we concentrated the need of operating point. In order to locate that operating point, the importance of DC load line. Operating point cannot be located individually unless you find the DC load line. So once again I am trying to concentrate the importance of operating point as well as DC load line. So I want to recall the important steps what we considered in the previous session. So I am trying to highlight the characteristics, output characteristics of CE configuration once again. So this is the output current ICE and this is the output voltage VCE. Of course, the output characteristics of the transistor will be like this. Obviously, we can locate the three important regions. One is active region, and another one is saturation region, and another one is cutoff region. This is active region, and this is saturation region. Of course, this is cutoff region. So in the previous session, I concluded that active region can be used as an amplifier if you work out the transistor in this region, and the saturation region can be used as an on switch, and as well as cutoff region can be used as an off switch. Anyway, if I want to find out that on which region the transistor is operating, we require the DC load line initially. So first I am finding the DC load line, the 2 points where DC load line will explains the maximum current and the maximum voltage of the transistor. The DC load line will indicates IC maximum as well as VCE maximum. Unless you locate the DC load line, of course it is not possible to locate the operating point. So on this DC load line, we are trying to locate the operating point. Obviously that already we are coming across in the lecture 1, where the operating point is lying at the center of the DC load line, then the transistor is operated in active region. Otherwise it can be operated in saturation region or cutoff region. And one more thing is, due to implicit parameters or explicit parameters, of course this is the DC load line and this is the operating point, where the operating point is also indicating the output voltage as well as output current, whereas nothing but IC and VCE in that current situation. Operating point is also called as Q point. Q point will indicates, or Q point will inform us that on which region the transistor is operated. Anyway, due to some internal parameters or due to some external parameters, the output current is trying to change. Due to the physical properties of the transistor, externally the temperature is increased depending upon the transistor or amplifier which is operated in the environment. Obviously the operating point is trying to shift from active region to saturation region. For that purpose, I think in the previous session I am coming across one more important point, that of course designing the amplifier is not our work is completed. We have to see that whatever the amplifier we are using, I have to work out throughout the lifetime as an amplifier. Nothing but faithful amplification. Whatever the importance we are giving for faithful amplification, we have to give the same importance for stabilization also. So keeping the operating point at the center of the DC load line is an important task. For that purpose, I required the transistor biasing stabilization circuits. Transistor biasing stabilization circuits. In that process, some of the stabilization circuits we have to come across, in which the first one is fixed bias circuit, fixed biasing circuit. The next one is collector to base bias circuit. The next one is emitter to base bias circuit. The final one, self bias or voltage divider bias circuit. These are the prominent 4 biasing circuits we are using to keep the operating point at the center of the DC load line. Later we will try to discuss in detail about that. Among these 4 biasing circuits, we have to choose which one is the best circuit. This choosing of the best circuit can be defined by using parameter known as stability factor. Stability factor is also one of the crucial point what we have to consider in transistor biasing. By using stability factor, we have to identify that which one is the best circuit. In that process, before going to discuss in detail about the importance of each biasing circuit, let me concentrate that a little bit more time on biasing. What is the stability factor? How can we define the stability factor, and how can we find out the stability of any circuits? We will go for basic definition of stability factor from these considerations. Stability factor. It is a ratio of change of collector current with respect to change of reverse saturation current. Stability factor is defined by using letter S. It is the ratio of change of collector current with respect to change of reverse saturation current. Always we have to see that the value must be minimum. So stability factor is defined as change of collector current, change of reverse saturation current. If you carefully observe this definition, the output current should not vary with respect to the variation in the reverse saturation current. Always we have to see that if the change is minimum, then that circuit is more useful. So change of collector current must be affected only by the variation of input current only. If the output current is changing with respect to reverse saturation current, means we are getting very high stability value. If the stability value is high, means that circuit is not suitable for practical scenario. So that's why first we will try to calculate that what is the stability factor. This is the basic definition of stability factor, but actually stability factor is depending the type of configuration what we are using. So more or less that already I am coming across in the previous session also. For time being, I am considering a transistor biasing circuits with a basic consideration example as common emitter configuration only. Of course, we can use common base, common emitter as well as common collector. For time being, I am considering only common emitter configuration only. Why we require the stabilization circuit only in common emitter configuration? That we will try to see little bit more analysis on stability factor. So if you carefully observe that the operation of a transistor, basically from the broad line, from the bottom line, we can say that the operation of a transistor is like an water pipe, where we are trying to send the water from source to destination. This is the source and this is the destination. Is there any hole in between source to destination? Whatever the water we are sending, it is not reaching destination properly. It is trying to go on this hole, and the remaining water is coming to the destination. The operation of a transistor is almost all equivalent to this example. For example, you consider the emitter is nothing but source and the destination is nothing but collector, and the hole whatever it is forming between source to destination is nothing but base. So in this example, I am considering total emitter current is equal to base current plus collector current. Always if the hole size is minimum, so that we can send the total water from source to destination. Always I have to see that the size of the hole is minimum, so that we can send the maximum water from source to destination. Here also always we have to see that the base current must be minimum, so that IE is approximately equal to IC. That is my aim. The total electrons whatever I am sending from the emitter, I have to reach the collector by maintaining the minimum base current. From this operation we concluded the different configurations like CB, CE and CC. Each configuration having its own amplification, where CB we are using alpha, whereas in common emitter we are using amplification factor as beta, and in common collector we are using amplification factor as gamma. Now we will try to see that what will be the output, of course, output current equation of a transistor on each configuration. For example, you consider for CB configuration, in CB configuration, the output current IC is equal to alpha IE plus IC B naught. So this is for CB configuration, where in CB configuration output is collector and the input is emitter, and the base is common in between input and output. This is the transistor equation where IC is equal to alpha IE plus IC B naught. If you carefully observe that output current of a common base configuration, IC is equal to alpha IE plus IC B naught. This is majority carrier current. These are majority carriers and these are minority carriers. So that's why it is called BJT, bipolar junction transistor. Anyway, now we will try to see that why CB configuration is more stable compared with CE configuration. That is my aim. My aim to prove that why we required the stabilization circuit for CE configuration only. Why stabilization circuits is not necessary for CB configuration. That analysis I am trying to discuss, or I am trying to spend more time in this analysis, that why CE configuration is having less stability compared with the common base configuration. In that process, first I am trying to find the stability factor. So I am taking the current equation of common base configuration. So currently I am concentrating of common base equation. For stability factor, you consider this as equation 1. Differentiating equation 1 with respect to IC naught. Differentiating both sides with respect to reverse saturation current. Differentiating both sides with respect to reverse saturation current to equation 1. So after differentiating both sides with respect to IC naught for equation 1, so IC is equal to alpha IE plus IC B naught. So I am differentiating IC with respect to IC naught. Of course, alpha IE differentiating with respect to IC naught. Of course, this IC B naught differentiating with respect to IC naught. This quantity is becoming as 1. Why? Because IC naught is equal to IC B naught. So differentiating numerator and denominator with the same value, the resultant is equal to 1. Where in IE plus IB plus IC, from the transistor equation, we conclude that IE is constant. It is fixed value. So from this IE as constant, differentiating the constant, the value is 0. Then differentiating IC with respect to IC naught is nothing but stability factor this stability factor is equal to 1. That's why the common base is more stable. Common base is more stable. Why? Because the stability factor is unity. Let me conclude that common base is more stable after defining the stability factor of the common emitter. Okay, that we will try to see that the transistor equation of common emitter. For common emitter configuration, as you know that IE is equal to IB plus IC from the definition of a transistor, and from the common base configuration, IC is equal to alpha E plus IC B naught. This is from common base configuration. This is equation 1 and this is equation 2. Substituting equation 1 in equation 2, so that IC is equal to alpha. In the place of IE, I can consider it as IB plus IC plus ICB naught. So now I am trying to separate the IC terms on one side. So IC is equal to alpha IB plus alpha IC plus ICB naught. So IC of 1 minus alpha IB plus ICB naught